Good afternoon, everyone. Thank you for coming to the ISSST forum. My name is Jingshu Zhang from the Material System Lab of Massachusetts Institute of Technology. And today I'm going to talk about a global demand forecast for the platinum group metals in the automotive industry. For those of you who are not particularly familiar with the periodic table, the platinum group metals are a group of metals located as follows. There are 6 different elements in the platinum group metals, and the 3 darkened ones, platinum, palladium, and rhodium, are used most widely in the automotive industry because they are excellent catalysts that can be used at relatively high temperatures and are stable in many aggressive chemical conditions. The platinum group metals are important for vehicle emission control as catalysts, and 48, 82, 93% of platinum, palladium, rhodium respectively are utilized in the automotive industry. Therefore, a supply shortage or a changing regulation or advancing technology may result in scarcity risks. It is important to understand the various scarcity risks and to have flexible design to mitigate the adverse effects of supply shortages. So we have developed a simulation approach that will yield the global demand for the platinum group metals. It might look a little bit daunting at first glance, but I will walk you through this entire model step by step. We follow the Lucas critique, where macroeconomic forecast has to have micro foundations. Therefore, we first look at the PGM price technical options and performance requirements to obtain a cost minimizing set, and use that cost minimizing set as the decision constraint to determine how much PGMs we want to use per vehicle. Then we multiply the micro data, which is basically PGM weight per vehicle, with the global fleet of vehicles per year to get a PGM global demand per year. Let's jump right into technical options first. So we have done a meta-analysis where an extensive literature research is done to obtain the compositional variations of platinum and palladium conforming to a certain standard. For example, here we have Euro 5 as our fixed standard. We look into literatures to see what combinations of the weights of platinum and palladium will yield a combination of catalysts that conform to this standard. And we do an extrapolation to get the curve that corresponds to how much of each minerals we have to use, and we sum them together to aggregate the total weight. Some of you might wonder why rhodium is not included in here. The reason that I didn't include rhodium in here is that their functionality in catalyst is very limited. They are only utilized to reduce the NOxes, and the amount requirement for them is quite constant throughout the time. So for now, we just ignore rhodium and focus mostly on platinum and palladium, which is used more extensively, as I will show you in a minute. And also, they are substitutable goods to some extent. Therefore, it is very interesting to examine when there's a price change for one commodity, what kind of impact of the demand of the other commodity will be. Then we look at the performance requirements. We want to know which components need these platinum group metals. If we look at the gasoline engines, it is mostly composed of the red bar, which is palladium. Whereas if we look at a diesel engine, which is composed of 3 components that use extensively of platinum group metals, the DOC, which is diesel oxidized catalyst, the CPF, the catalytic particulate filter, and the LNT, the linked nitrous trap. The green bar is predominant, and the green bar corresponds to platinum. Therefore, in a nutshell, the gasoline engines use palladium the most, whereas the diesel engine uses platinum the most because it has to operate at a higher temperature and due to other oxidizing constraints. Palladium is not yet suitable for diesel engines. As a statistical rule of thumb that we have observed through examining the literatures, we have noticed that there will be a 0.008 ounce of PGM loading increase for each additional level of regulation. Then we look at the PGM prices. Some of you might observe that after about 1995, the originally seemingly co-integrated platinum and palladium spot market prices started to diverge. The reason that there is this structural change is because Russia put a ban on palladium export, and Russia used to possess about 50% of the total palladium production in the world. Therefore, an embargo of export exercised by the Russian government caused a 380% of price increase in the platinum spot market price. At this moment, we'll just assume that there is no political risk, no disruptive technology, etc. We just look at a relatively simplistic model where only macroeconomic risks, namely the inflation rate, exists. We will add scenarios later to make our model richer. The historical platinum-palladium price ratio determines the strategy makers or the firm-level decisions preferences. As you can see, the price ratio also varies quite a bit, where the mean of the price ratio is typically around 3, and you can go to as high as 5 as the 95th percentile, or as low as 0.9 as the 5th percentile. We have done a time series study on the platinum and palladium time series, the price ratios. We used the auto-regressive integrated moving average model to obtain an optimal time series prediction of the platinum and palladium prices, and we also impose standard deviations on them to allow for uncertainties. As you can see, the price ratio tends to decrease according to this forecast, and this time zone extends to 2030. The reason for that is currently it conforms to current belief that people are going to substitute away from platinum for more palladiums because their prices are much lower, as you can see, because the price ratio of platinum over palladium is has an average of 3. So people want to use more palladium in the diesel engines, and that will increase the demand for palladium, which consequently drives up the price for palladium, resulting in a decrease platinum over palladium price ratio. After examining these 3 individual pieces, we can integrate them together to obtain a cost minimizing set. The cost minimizing set is obtained by using the forecast prices of these commodities times the weight each mineral is required to conform to a certain standard, and we sum them together to get the aggregate total cost of the catalyst. And then we use optimization to iteratively find the minimum price, assuming that firms are cost minimizing in their very nature. And in this case, we probably want about 40% of palladium and 60% of platinum. And we did that for each year into the future to construct the forecast. For firm-level decisions, there are 2 decision horizons. The first is called the decision year. That means the time it takes for the firm to realize that there's a price change in the market. Typically, we assume the decision year to be minimal because any managers or employees that are not laying back will realize that there is a market price change, and they will respond to the price change and adopt the optimal composition of the platinum and palladium catalyst. The reaction year, though, is a little bit more complicated. It means the time it takes for the catalyst to reach a certain optimal composition. It requires a lot of negotiation within the company, and it involves communications to the research scientists, and it involves research and development process, and involves costs. Therefore, as you can see from this illustration, the longer the decision year, say the optimal composition is 80%, but currently we are at 60%, the longer the reaction year, the longer it takes you to reach that optimal composition. Repeated measure analysis of variance indicates that a decision year of 0 years, which means people realize there's a price change instantaneously, and a reaction year of 2 or 3 years yield optimal results. If the reaction year is more than 4 and 5 years, it seems that their reaction is a little bit too slow and they are not responding to the market price fast enough. But if the reaction year is 1 or 0, they are probably following too much of the volatility of the market, which is not that predictable, and it takes a lot of money and effort and time to follow that trend. Therefore, it is probably best to opt for this golden mean of 2 or 3 years. Then we look at a vehicle number per year. The fleet number forecast and also of the past historical data are obtained from the Rio Tinto vehicle number survey. The vehicles are typically broken down into diesel, gasoline, diesel hybrid, gasoline hybrid, and electric vehicles with decreasing amount of requirements for the platinum group metals. The model is flexible to change the vehicle breakdown's respective proportions or even add new types of vehicles. The model is also broken down into regions: North America, Europe, Japan, China, one of the biggest developing economy in the world right now, and the rest of the world. Then we look at the PGMs per vehicle. I have basically already delineated how do we get the PGM amount per vehicle using cost minimization optimization, and the optimal composition is estimated using the time series price forecasts, and that price informs the decision makers how much platinum and palladium individually they need to use to conform to a certain standard. And for the gasoline engine, the major component that use primarily platinum is the three-way catalytic converter, whereas the diesel engine uses lean nitrous trap, diesel oxidation filter, a catalyst, and the catalyzed particulate filter. We aggregate all three components to get the total platinum group metals demand. Finally, we reach the last stage of the model. We can forecast for the global PGM demand per year. We used the data before 2006 to train the model, and we used the model to forecast for within sample, out of sample years, to see how the model performs with respect to reality. Here you can see that our model forecast moves pretty correspondingly well with the reality, but the reality has a huge dip in 2008 due to the financial crisis, and that dip is not fully captured by the MSL, by our prediction. The reason for that a little discrepancy there is because our model, as I have indicated earlier, does not capture the macroeconomic disruptive forces, say a financial crisis. We are only considering the inflation rate, so this is not taken into account. Similarly, for palladium, it models it quite well, and the palladium commodity demand wasn't influenced as severely as the platinum. Therefore, it actually captures quite well of the decrease in 2008 and the increase in later years. Apart from that, we also want to know what will happen if the price ratio changes. So basically, we assume that there's going to be a change in the price ratio in 2005. We carry out a Monte Carlo simulation for the spot prices of 2015, and based on the time series mean and variance up to that point, and obtain 5 scenarios. The first is the mean, the second, third mean minus plus 1 standard deviation, and the fourth and fifth mean and plus and minus 2 standard deviations to get different price ratios. And then we forecast what will the global demand be. One thing that you can immediately observe is that the higher the price ratio, meaning the platinum is much more expensive than palladium, then people will tend to respond to this incentive and substitute more palladium for platinum. Therefore, the palladium global demand will increase a lot, whereas the platinum global demand will decrease. But it is also important to realize that the trend for global demand increases for both commodity in the long run, despite of this short run disruption because of price ratio variation. We also look at a whole spectrum of platinum-palladium price ratios, and we look at how much proportion of platinum is going to be used for different price ratios. So platinum proportion has been quite stable from 4% to 10%. Within this price ratio range from 1 to 4.5, which is basically the 5th to 95th percentile of the price ratio variation in history. Whereas the diesel engine almost exclusively uses platinum, which corresponds to my earlier indication that a gasoline engine uses mostly palladium, little platinum. Diesel use mostly platinum, little palladium because of the environmental constraints. But if the platinum price happens to rise to such an extent that it goes way beyond 4.5, the historical maximum, then it is likely that we will enter a breakdown regime where people increasingly switch away from platinum. But from what we have observed historically and also in the forecast where the price ratio tends to go down, it's unlikely that in the future we will see the price of the platinum go that high. Therefore, just to summarize, we have done a techno-economic model constructed using both meta-analysis and optimization, but mostly on cost minimization. The price ratio, it turns out, is critical in determining the future demand for platinum and palladium. Palladium is prone to wilder swing when the price ratio shifts. The reason for that is the palladium is not as strong a catalyzing agent as platinum. Therefore, the moment you switch away one platinum atoms, you probably need to add in 2 or 3 palladium atoms to compensate for the absence of that platinum atom. Therefore, if there is a demand shock, as we have seen earlier, the platinum demand rises a lot more than palladium. And lastly, the gasoline engine primarily uses palladium and diesel engine primarily use platinum, absent technological innovation in the future. And that concludes my presentation, and I welcome any questions. Thank you.